So in this lecture, we're going to just quickly look at what happens when we deoxygenate ribose. And so let's do the deoxygenation of ribonucleotides. So if you recall, we need to lose the oxygen atom at that 2 position. The 2-deoxy sugar will then give rise to our deoxy ribonucleic acids that we use to make DNA. Okay, so how we start is we're going to focus now on the ribose side of things. So we have N base up here. We have CH2O, and it says we're going to go with the diphosphate. Sounds good. We now have OH and OH. We're going to consider now is the up hydrogen here, and that's going to interact with a cysteine residue that is shown as a free radical. These aren't hard to get. Cysteine is, sulfur, excuse me, is a nice radical stabilizer. And so we can get cysteine radicals quite easily. This is called a thiol radical, and this can be generated by an enzyme. So anyway, we're going to abstract a hydrogen. We're going to have 3 fishhook arrows to show that abstracted hydrogen. That's going to put a dot at the C3 position, which I know it's not the C2 position. So we have to kind of do some work on both sides to get that OH off. Deoxygenation in general is pretty tricky. Okay, now we're going to let some other sulfur atoms from some other cysteines that are in close proximity to each other get involved, and namely we're going to have a proton transfer occur where the OH gets protonated, and it says, shoot, I grabbed the wrong hydrogen here. We're going to go over here. Okay, that's going to put a proton on the 2OH, that OH that we ultimately want to lose, and now it has become a good leaving group because it is on, it's an H2O. So we can just let this walk away, and we've lost our oxygen. I mean, we're not at a stable species by any means. We have a radical on one side, and now we have a positive charge on the other side. Okay, so what do we do at this stage? Well, here we're going to consider an interesting resonance structure. If you recall, radicals next to charge, the radical can kind of jump over to one side and push the negative or positive charge on the opposite side. That's a weird resonance structure, but it's a resonance structure indeed. So I'm going to have my resonance structure arrows, and what I'm going to do is, instead of considering the remember, this is not an equilibrating structure. This is a resonance structure. Instead of considering the resonance structure where the positive charge is on the right and the radical is on the left, I'm going to flip them. That's going to put the positive charge at this position. And now we're going to see more sp2-like character on the on this carbon as we absorb electrons from the OH bond, and we could have a base come in if we need to, but it's a pretty acidic hydrogen, because if we lose that, we can take the electrons down to form a carbon-oxygen double bond, and we get a full-blown ketone in our sugar now. We still have a radical on this right position. Okay, now this radical is going to take a hydrogen from the sulfur that was not deprotonated on our, excuse me, that's a negative charge, isn't it? This is going to grab this hydrogen to make a radical. And now we've fully deoxygenated our 2 position. And so what we have to do at this point is just deal with our ketone oxidation state to get the appropriate alcohol oxidation state again. And to do that, we're going to rely on this sulfur radical system. Now, this took me a little bit of practice to draw. At this point, I'm going to zoom in here. I'm going to have a lone pair come down and a lone pair come down and 1 electron come down. And that's going to make a sulfur-sulfur radical. Which is going to be helpful for the upcoming structure. Excuse me, a sulfur-sulfur bond. Now, on this lower oxygen, I still have 2 lone pairs plus a lone electron. This is actually negatively charged, whereas the above sulfur is neutral with 2 lone pairs, same group as oxygen, recall. But the point is this is this has 1 too many electrons. That's giving it a radical character, which isn't good. That's giving it a negative charge character that isn't good. So what we're going to do is an SET reaction, which is a single electron transfer. So I'm going to pick up that radical. I'm going to show it with an arrow. Is that what I should do? I'm just checking the book. Let's see. So they, just want to make sure, wait. Oh yeah, that's what I want to do, but I'm just trying to think. So we're going to just show this as, I'm trying not to make this confusing. I'm probably doing a bad job. I'm going to take this radical, and I'm going to plop it in here, and then push these 2 electrons up. So you can think about that as the carbonyl resonance structure with a positive charge. Let's just stick an electron into that positive charge of that carbonyl resonance structure. I'm going to draw it for a second and then just plop the electron in there, just so you can see what I mean. So we have N base here. I'm going to draw that positive charge just for a second. What I'm going to do is I'm going to take that radical, it was right here in the circle, 1 too many electrons, giving the sulfur a negative charge. And I'm just going to stick it right here. Now, if I do that, let's do this. I don't want that. I'm going to now cross out that positive charge because I have a radical present. Radical probably needs to be, well, no, let's leave it red. Okay. So the radical is now present, which means that carbon is now neutral. It's not an even electron species. It doesn't have 8 electrons, but it's formally neutral. Group 4 element minus 3 bonds minus 1 unshared electron gives us a neutral molecule. So that sulfur that was desperate to get rid of an electron, okay, has given it to the carbonyl. And now it is neutral because it's given, the sulfurs are now neutral. I could draw those once, sure. Cysteine, so now we have 2 sulfur atoms from 2 cysteines. That's a disulfide bridge, blah, 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 blah. Biochemistry. Okay. Now at this point, what we could do is react this with an acidic hydrogen from somewhere, some residue to neutralize this position. I'm not going to draw that hydrogen anymore. All right. We still have a radical at this position, so that radical is going to pick off an H, and it's going to go in from the top. I'm just running out of space. And now that H is going to go on the top. Let's show that in blue. Okay. There's our deoxygenated nucleotide diphosphate. Now, what did we get at the end here? After the cysteine lost its hydrogen, we now have a sulfur radical, but this is from the beginning. We did it. Okay, so the sulfur radical is from the beginning. We use that at the outset of our reaction. If you, I'm just going to pan out a second. If you look at the I can't go that far. If you just look at the very first step, we needed a cysteine sulfur radical. And so we sort of turn over the enzyme by abstracting that hydrogen at the end. So that first step, we pull the hydrogen off of the 2 position. In the last step, we put the hydrogen back on, this time in the 3 position, to get us to, I guess we started by pulling off the hydrogen at the 3 position. We put the hydrogen back on the 3 position in the last step. Anyway, I like this. This is fun stuff. You ultimately get your deoxygenation. So if something is deoxygenated, that means we reduced our system, and then the net thing that was oxidized, or 2 cysteines, were oxidized to make a disulfide bridge. That's kind of our net redox neutral event that gets us there. But we've now deoxygenated ribose. We've completed the biosynthesis of our deoxynucleotides to build up and make cool DNA sequences that can form a double helix, communicate information genetically, tell what genes should be copied, and that sort of thing. Okay, anyway, that'll do it for this lecture, and that'll do it for this unit. So hopefully you enjoyed it. I know it's a lot of work, particularly in the last chapter, but hopefully rewarding. Okay, we'll see you later.